you, everyone. Thank you. Thank you, Tusha, for your very nice invitation and your kind words. And thank you all for being here for 2 hours and a half almost on your vacation. But yeah, it's great pleasure to be here. I heard wonderful things of IIT Bombay, and I've been in touch with several of you through email. So it's great to put faces to the email addresses and catch up with people I've seen before and visiting this campus and India for the very first time. So as you heard, my name is Emilio Martinez-Paneda. I'm an academic at Oxford, where I lead the Mechanics and Materials Lab, where Tusha was based. And in my group, we do both experiments and modeling. But just to complement a little bit the previous talk, I will shift gears a little bit and move more towards the modeling side of things. And I think one of the reasons I also wanted to talk about the modeling was that I believe that we have a unique opportunity now to basically crack some long all-standing problems that have been an issue for scientists and engineers for decades, if not centuries, and they are critical to many applications and society. And the three that I'll focus today are hydrogen embrittlement, lithium-ion battery degradation, and corrosion. And Tusha has done contributions to 2 of those at least, so I'll be highlighting those as I go along. So I'm going to try to cover a lot of ground. So I'll have to be here. I'm going to try to cover a lot of ground, so I'll have to be a little bit superficial. But of course, very happy to go deep into the details during the Q&A session. So again, we're going to focus on 3 topics: hydrogen embrittlement, lithium-ion battery degradation, and corrosion, in that order. And I think what I should say is that all of them have something in common. All of them have this, I would say, unique opportunity that we can finally resolve this couple of problems. So I think the things that they have in common, of course, is that they're interfacial problems, and there are a couple multi-physics problems. And they're problematic. They're difficult to understand. They have complex physics. And they're very interdisciplinary. You need to understand material science, you need to understand mechanics, chemistry, electrochemistry, condensed matter physics, and so on and so forth. But I think there's a unique opportunity to crack these problems now from a modeling perspective. This is what we want, to predict how things are going to behave in time and space. And the opportunity comes from, in my opinion, 2 reasons. The first one is coupled multi-physics modeling. So if we think of a general stress corrosion cracking problem, you have something like this. So you have some sort of metal that has been subjected to mechanical loads, which contains some sort of defect. It could be a pit, a crack, any other defect. That is exposed to an aqueous electrolyte where there's multiple ionic species that are moving around due to fluid flow, due to electromigration, due to diffusion. Then lots of things are happening as well in the surface, in the interface between the metal and the electrolyte. You have reactions due to corrosion. You're losing metal atoms. You have reactions that bring hydrogen atoms inside of your metal. Those hydrogen atoms move around within the metal, within the crystal lattice, driven by gradients of hydrostatic stress, so coupled with the mechanics. They embrittle the material at multiple scales. They change dislocation mobility, atomic bond strength. There's many things happening in here, and all of them are quite strongly coupled. So you cannot just ignore half of them and hope that you will get to the right location. But I think that there's a good opportunity to tackle these problems, because finally, computer power is big enough that we can actually handle, kind of by brute force, all the equations that describe all these physical phenomena. So you can see some examples here. So if you're interested in the behavior of aqueous electrolytes, you saw in the Planck equations. Those of you working on batteries or electrochemists will be very familiar with this. You have also equations, of course, for the formation of the material, hydrogen transport, surface reactions. So each of the communities involved in this multidisciplinary problem knows what are the partial differential equations that describe each of the phenomena. And this is good news, because if you look at these equations, you'll see that they're kind of physically based. Right? You are explicitly resolving the physical processes involved. So if I look at Ernst Planck, you have transport due to fluid flow, diffusion, electromigration. And as you can see, all of them rely on parameters that have a clear physical meaning and that we can independently measure in our labs. So you have diffusivity, temperature, Faraday's constant, and so on. So there are no alpha, beta parameters that you magically fit to an experiment. These are all parameters that you know before you run your calculations. This is the idea. So we want to be predictive, and in order to be predictive, we need to be mechanistic. We need to resolve the physics almost like brute force. And the growth of computer power gives us that opportunity. You can see in blue some of the nodal degrees of freedom. So you're solving for 10, 15 degrees of freedom in your model per node. But nowadays we can finally do those things. And that's good, because then we can reduce assumptions and we solve the physics as they happen in reality, as a function of material parameters, diffusivity again, parts per molar volume of hydrogen that we know before we run our calculation. So we don't need to recalibrate, fit things around, and we can extrapolate and interpolate between data. So this is one of the I think opportunities that we have in front of us. The other one comes from the next challenge, which is the fact that this interface is not stationary. It's not there sitting down there. It's evolving in time. So whether you have a crack or a pit, your corrosion front, things are moving around. And the more they move around, the more complicated it becomes because everything is strongly coupled, right? If I have a defect that is sharper than other defect, then that will mean higher stresses, as you all know. But also, the electrochemistry inside of the defect will change depending on the shape and morphology. And at the same time, how this defect grows will depend on the local mechanics and chemistry. So everything is very strongly coupled, and you need to resolve this morphology. And the good news there is that we have now computational techniques that allows us to simulate interfacial problems of arbitrary complexity. I'll be discussing this. This is what we call phase field modeling. Some of you are very familiar with this. I'll be discussing this in the context of fracture mainly, but also I will apply it to other problems like corrosion or voiding in solid-state batteries. But the idea is quite simple. So whenever you have two phases, let's say like a blue phase, which could be uncracked material, and a red phase, which could be cracked material, you could describe the interface in between as sharp or discontinuous, or you can smear that interface over a finite domain and use an auxiliary variable, the phase field, to describe where the interface lies. And then you just need to define an evolution equation for the phase field based on whatever physics you're interested in. And by doing that, through this implicit representation of interfaces, you can capture interfacial problems of arbitrary complexity. It's really a new horizon when it comes to modeling interfaces. There's multiple advantages. Three that I always like to emphasize is that you're solving your interface equation in the entire domain. So there's no need for moving boundary conditions to see where things are. You treat it all in the same way. Topological changes such as divisions of merging of interfaces, imagine cracks coalescing into each other, crack branching, all of those are naturally captured without any ad hoc criteria, any ad hoc condition. And finally, convening to the problems that I'll discuss today, this interface equation can be naturally captured with multiphysics phenomena, with other equations describing other physical phenomena. You know where your crack lies, and you can combine very nicely this with other equations. And I mean, this method, I know many of you have heard about it already and work with it. It's been a revolution in many areas of science and engineering. It has been by far the most widely used technique in macrostructural evolution. It is becoming the dominant technique in fracture mechanics. I was at WCCM in July in Vancouver, and 95% of the talks on computational fracture mechanics were using phase field. And you can see why here, right? This is blue. This is the outcome of a simulation. Blue means intact material. Red is cracked material points. This is hydraulic fracture. That's why you see such a funny looking cracks. And you can see the very complicated cracking phenomena can be captured. Yeah, crack coalescence, crack branching, nucleation of secondary cracks. This is something that we couldn't do. And you can do that in 2D and 3D. This is something that we couldn't do with other techniques. And finally, we have recently shown, together with other groups around the world, that you can extend this phase field paradigm to corrosion, to predict the evolution of the corrosion front. So you use the phase field to describe the interface between the aqueous electrolyte and the metal, the dissolution of material. But let me tell a few things about phase field fracture, because that's something that will come up through these applications that I want to discuss today. So because I think one of the strengths, or one of the reasons why 95% of those talks in this World Congress on Computational Mechanics were based on phase field is not only because it allows you to simulate very complicated cracking phenomena, but it's also because it's physically sound. So the nice colors that you see in your computer agree with experiments, agree with reality. And this is because phase field provides a platform for Griffith's energy balance. So everything is based on the thermodynamics of fracture. So those of you who have seen fracture mechanics will remember that Griffith, one of the fathers of the field, he postulated that in order for fracture to be consistent with thermodynamics, for a crack to grow, the energy stored in the material had to be equal or larger than the fracture energy, the energy required to create two new surfaces. And you can postulate that energy balance in a variational form. This was done by some French mathematicians. And then if you're able to minimize this functional, then you're able to capture the evolution of cracks as an exchange between energy stored in your material and fracture energy. And this is not so easy to do when it comes to computers, because you need to keep track of where your interface lies. But here's where the phase field comes to a rescue. And then we can regularize this functional and use the phase field as a marker, kind of like a damage variable, to tell us whether we have a crack or intact material. So for example, the phase field equal to 0 could be the intact material point, and then 1 would be fully cracked material points. And in a way, it's kind of a non-local continuum damage mechanics model. You can see that there's a gradient and therefore a length scale. which means that your results are going to be mesh independent if your mesh is fine enough to resolve, the interface. But you're going to have mesh independent results, which is quite convenient compared to most damage mechanics models. And then, of course, similar to this kind of damage mechanics concepts, you are degrading the stiffness of your material. So when the phase field is equal to 1, you cannot carry any load. And this is basically what the strong form of the equations look like. So at the top, you have the equation that you normally solve in finite elements, the balance of linear momentum, with the phase field degrading your load carrying capacity. So as phase field goes towards 1, then you have fully damaged material, you cannot carry anything. And then basically the only extra thing that you have relative to your usual finite element implementation is this extra equation here, which is basically the evolution equation for the phase field, which is basically a competition between the energy stored in your material, which is the strain energy density, something that comes from the mechanical problem, and the toughness, a material property that characterizes the resistance to fracture of your material. And just by solving this additional differential equation, you're able to capture very complicated cracking phenomena on the original finite element mesh and without convergence issues. It's a very robust method. And I won't get too much into the details of why it's robust, but we can discuss that afterwards. You can see an example here. So this is a calculation running my group. This is crack branching due to the application of a dynamic load. So due to the interaction with the waves, you can see that the crack branches. I'm going to use always blue color to denote intermaterial and red color to denote the cracks. And you can see, that the model, I don't need to make any decision on where the cracks go. The model will, find this most convenient energy path and predict the growth of the crack. And I mean, there's no surprise this method has been enjoys such a popularity in the computational fracture mechanics community. I myself have worked with XFEM, some models, remeshing, many other methods. I never found anything as exciting as this. You can see some examples here. So this is comparisons for metals, ceramics, rocks, composites, functionally graded materials. And you can see that not only you can capture very complicated cracking patterns in 2D and 3D, but you also do that showing a remarkable agreement with experiments. So I think this is, why we all feel quite excited about this. And my goal was to extend this to other applications, to a couple problems, basically. So let me go back to the table of contents. So let me start with hydrogen embrittlement. The good news is that you heard already a nice talk about hydrogen embrittlement. So you're all, even those of you not working on the area, are familiar more or less with the problem. So I won't spend much time on the motivation. I think the only thing I would say is that there's an increasing interest, of course, in this topic. It's becoming suddenly a very hot topic because of the role that hydrogen is going to play in decarbonizing many applications and sectors, including some that are known to be particularly difficult to decarbonize, such as aviation or steel making. So whether we like it or not, if we want to go for full decarbonization, we're going to need hydrogen. And there's consensus on that. There's a bit of debate on how much hydrogen you'll need and how many applications will be electrified or decarbonized using hydrogen. But there's consensus that hydrogen is absolutely essential. And therefore, there's consensus that we urgently need to deploy a hydrogen energy infrastructure that currently doesn't exist. We have some infrastructure for electricity, but we have nothing for hydrogen. So we need to build this infrastructure. And as you heard in the previous talk, this is going to be a challenge because, storing and transporting hydrogen is complicated because metals become very brittle as a result of this. And this is something that we know since a long time ago. This was a paper published in 1875, 150 years ago now, in the Proceedings of the Royal Society, where Johnson speaks about some remarkable and extraordinary decrease in toughness and strain in the presence of hydrogen, in iron and steel in the presence of hydrogen. And I mean, the effect of, you saw it in the previous talk, the effect of hydrogen in metals is really remarkable and extraordinary. Just to remind you of some of the key phenomena, this is the effect of ductility, uniaxial tension curves, and you can see how the failure strength is very significant to reduce when you expose your metals to hydrogen, in this case, hydrogen gas. The reduction in toughness is even more impressive. This is fracture toughness for a pressure vessel steel. You can see that 6 parts per million of hydrogen, so a tiny amount of hydrogen, can bring your fracture toughness from above 220 megapascals per meter to below 20 megapascals per meter. So an order of magnitude drop with a tiny amount of hydrogen. And this is a pressure vessel steel, so very relevant to hydrogen storage. And these are pipeline steels. This is fatigue crack growth rate, so crack velocity in a log-log plot. And you can see that in the absence of hydrogen, you are here. But the moment you bring hydrogen to the picture, you increase by at least an order of magnitude, the crack velocities in hydrogen-containing environments. So that's, of course, a challenge. You have very ductile metals behaving almost as brittle as ceramics, and you need to store and transport hydrogen. You need to deploy this infrastructure quickly, and you need to figure out under which conditions this infrastructure can be used. So I think that models can play a big role because models allow us to quickly test conditions, quickly test ideas, and quickly map safe regimes of operation. So this has been our goal. And basically, this is what you want to model. So you have some hydrogen atoms coming into the material. Those hydrogen atoms travel through the crystal lattice. They are sequestered or trapped at some microstructural defects. And then eventually, when they are trapped in critical interfaces, they cause fracture. This is kind of the schematic. Let me maybe play it once again. So this is more or less the big picture. So you have hydrogen coming into your metal, coming from anywhere. It could be gas or electrochemical environment. I'm not going to discuss that. We do a lot of modeling on that front as well. Olivia discussed some of it, but I don't have the time to go through it, so I'm just going to skip that one. Let's assume that we know how much hydrogen is coming into our metal. What we're interested in is in the transport of hydrogen and its accumulation at critical interfaces. So if you wanted to model this, the simplest way you could think of is using this kind of phase field technologies. We could think of solving a three-field problem. So you will solve for the deformation in the material, the equation I showed you before, the hydrogen transport equation, and then the damage. And I'm highlighting here some of the coupling. So of course, again, the damage will reduce your load current capacity, as we said before. The hydrogen transport equation, you can see here, hydrogen moves driven by gradients of concentration, but also by gradients of hydrostatic stress. So the coupling with mechanics is quite strong. And then finally, you have the damage, which evolves based on the energy that you're storing in your material, but also your resistance to fracture, which will be dependent on the hydrogen concentration. This is the strong couplings. So let me discuss them a bit independently. If I focus on first the coupling between mechanics and hydrogen transport, I've showed you the simplest equation one could use. In reality, the hydrogen not only travels freely through the crystal lattice, it's also sequestered or trapped at microstructural defects. So you can expand your model and add not only a lattice hydrogen concentration, but also a trap one. And then how this evolves depends on Oriani, McGrath-Foster. There are a wide range of models that assume either thermodynamics or some sort of kinetics. But I think, again, what I want to emphasize is the coupling with mechanics. You can see that the steady state solution is something like this, where you have an exponential term with a hydrostatic stress inside of that exponential term. So the hydrogen concentration is going to be very, very large near cracks and other stress concentrators. But then when you implement this into finite elements, you get behavior like this. So these are just, some representative results. Here you see a pipeline where we're increasing the hydrogen, the pressure of hydrogen in the inside, and you see how the hydrogen distributes. This is another pipeline with various defects and components, and this is within the microstructure. So whenever you implement this coupled deformation diffusion model, which is relatively straightforward to do, even in commercial finite element packages, then you can predict the distribution of hydrogen within your component and within your microstructure. But I want to spend a bit more time on the damage process itself. So now you know how much hydrogen you have, where and when. And the idea is to see how this affects your resistance to nucleate and grow cracks. And there's a couple of ways you can do that. And we have proposed two ways. One would be, the good thing is that the framework is quite universal. So whatever way you want to reduce your fracture energy, you're welcome to try it. And many groups have taken our framework and then expanded in multiple directions, because there are different interpretations on how hydrogen actually degrades your fracture resistance. And also this can change between the material and environment. But the two approaches that we have basically pursue are on the top, the more mechanistic approach. So we try to understand the physics of this problem. We try to come up with a degradation law that did not rely on extensive experimental calibration. And to do that, what we do is we basically solve the couple problem. This allows us to predict how much hydrogen we have in a critical interface. Let's say that you're interested in a grain boundary. So solving this deformation problem, I know how much hydrogen I have on my grain boundary. And then you do atomistic simulations. These are DFT calculations for two types of grain boundaries in nickel. And then you can come in here with your grain boundary occupancy, and you can directly quantify what is the reduction in fracture energy or surface energy for that particular hydrogen concentration. So in that sense, you don't have to fit anything. There's no calibration involved. You just need to do one atomistic calculation once in your lifetime offline, and that's all you need. So this is the more mechanistic approach. Often working with industry, they tell us they don't trust atomistic calculations. And they say, oh, we also are working with materials, that we know very well, that we characterize under fracture under a very wide range of hydrogen conditions. So for example, these are for pipeline steels, and there was a question before of comparing multiple pipeline steel grades. So you can see here, for given hydrogen pressure and hydrogen concentration, how those pipeline steels go down. And so they say, oh, okay, we don't need to do atomistic calculations. Why don't you just feed the data that we have and put it into the model? And that's also a possibility. This would allow you to, develop from first principles new hydrogen resistant steels. But if you're interested in, understanding the behavior of these materials and their, map safe regimes of operation, this is also suitable. And a lot of the big questions that are happening now in the hydrogen community are related to technological problems that involve materials that we know quite well. So let me show you some results. Before I do so, let me show you another aspect that I haven't mentioned before, which is another aspect of the coupling. Now, we're not only interested in the initiation of cracks. For that, you probably can handle well with the stress intensity factor approach. We're interested in the propagation of cracks. And when you look at the propagation of cracks, then what you care about, or you need to make sure that you capture how the hydrogen the hydrogen environment follows the crack. If you imagine that you have a pipeline in seawater or in hydrogen gas, the moment the crack propagates, the fluid is going to immediately occupy that space. It's going to immediately become into contact with the newly created crack surfaces. So you can do that. This is on the top, you see the phase field growing, and here you see the hydrogen concentration. You can see, by the way, how eventually it accumulates also near the crack tip, near the hydrostatic stress field. But you can see how, as the crack propagates, the hydrogen environment can follow. And there's multiple ways you can do it computationally, either through a penalty approach, for example, or by enhancing your diffusivity in the regions where the phase field is larger than 0.9, for example. So this is the beauty of phase field. You always have full control on what your damaged regions and undamaged regions are without any special treatment. So let me show you some representative results. So what you see here are pre-charged steel bars. These are high-strength steel bars that were exposed to a hydrogen-containing environment and then tested under uniaxial loading. They had notches. And you can see that the symbols, which are the crosses, fit nicely the model, or the model fits nicely the symbols. These measurements of notch tensile strength versus hydrogen content. So we are quite happy with the outcome. This is just some representative results of what you can get with these sort of coupled models. These are experiments done in Norway that were a bit more interesting. What they did here is they immerse duplex stainless steel samples in a seawater bath and subjected them to a constant load. And then they measured the time to failure of each of the samples. Since they were testing different loads, then they had different time to failures. But as you can see, all the samples failed relatively early. So they weren't able to identify what is the critical threshold load below which you will not see embrittlement. But with the model, we can reproduce those experiments in our computer and not only gain confidence by reproducing the experimental data, but also run virtual experiments over very large timescales, very quickly in our computer, very slow in the lab. That allows us to determine what is this critical threshold below which embrittlement will not happen. And you can do things, you can go up the scales, you can go down the scales as well. So we recently started doing a lot of work on crystal plasticity, the coupling with crystal plasticity and microstructural modeling. Traditionally, this was not of interest to the hydrogen embrittlement community because they were looking at very aggressive conditions where you had already big cracks to start with. But now when hydrogen compatible materials are being considered for aviation, there's a lot of interest in looking at what happens, how do you initiate a fatigue crack, for example. So in macrostructurally driven problems, so we're starting to do crystal plasticity and couple with these models. But you can also do, of course, large-scale simulations. So again, at the end of the day, these are mechanistic models, but they are finite element continuum level models. So you can apply them to model real components, and we're trying to bring this idea, this paradigm of virtual testing to hydrogen technologies. This is something that has not been used in hydrogen before. And quite excitingly, you can solve problems of arbitrary complexity. So you can create sort of digital twins of critical infrastructure. For example, what you see here is a pipeline. It's a very long pipeline characterized by BP. All of those wreck defects that you see there are pit corrosion defects. We can embed very easily those defects into our finite element model. We don't even need to create a funny mesh because you're solving for the phase field as a degree of freedom. So you can impose as an initial condition phase field equal to 1 where those defects lie, they have been properly characterized. And then we can subject the pipeline to in-service conditions. And as you can see here, we can see how those defects are growing, how they merge with each other, and eventually how you get the complete failure of your pipeline. So I guess the takeaway here is that these techniques are not only useful to model simple academic experiments. No matter what the complexity of your problem is, we finally have a tool that allows us to predict when hydrogen-assisted failures will happen as a function of the environment, the loading conditions, and the material. This is the takeaway. And we have extended this to fatigue. Here what you have is basically a fatigue degradation law that reduces your fracture energy, and we use this to obtain SN curves and also this kind of more fatigue crack growth rates, Paris law type of behavior. And I think the beauty of this is that this is a work that we did with one of our industrial partners, Tenaris, and we calibrated the fatigue degradation function with response in air, and then we predicted hydrogen-assisted fatigue for a very wide range of environments, different hydrogen pressures, different load ratios, different frequencies. So here, there's no recalibration of the model. We are basically just changing, the load ratio, the frequency, just the way we load our model. There's no fitting involved in any of these results. And as you can see, we were able to capture all the conditions that they have been tested before. If they change the loading frequency, the model will naturally capture that change in loading frequency. If they change the load ratio in the experiments and that increase the crack growth velocity, we will quantitatively be able to capture that effect of load ratio and so on and so forth. So I think, a lot of these things are mesoscale processes related to how quickly you load, how quickly hydrogen moves around, and those problems you can naturally capture in these models. And by the way, we have not only done fatigue calculations for lab scale tests, but also full scale tests. This is some tests that were done by a Japanese group, and they tested the full pressure vessels with different notches and different materials. And you can see that the number of cycles to failure predicted by the model and by the experiments, by the full real scale experiments, seem to be in good agreement. So we were quite excited, because if you can capture fatigue, then all the other problems become kind of toy problems. And just before I finish the hydrogen part, I want to showcase one case study that I think is of particular interest and where Tushar was heavily involved. This is one of the big questions in the hydrogen community: under what conditions will hydrogen transport pipelines fail? Because the goal is to actually, as soon as next year, start transporting hydrogen in the natural gas pipeline infrastructure. In fact, the Germans have started doing it 3 days ago. And basically what we're hoping is that we don't need to build new pipes. We're going to use the natural gas pipelines that we already have in place. And you can see here, this is the European hydrogen backbone. So these are the pipes the blue ones are the ones that are repurposed, retrofitted, and the yellow ones are the ones we're going to build. You can see places like the UK, we're basically hoping that we'll use the pipelines that are already there, because that will save, I would say, basically an order of magnitude in cost. So it will be 10 times cheaper to do so. But as you can see in this plot here, those pipeline steels, seem to be undergoing significant hydrogen embrittlement. You can see here the pressure. These are some of the pressures that people are hoping to transport, and you can see that you get a very significant drop in fracture resistance. So the key question is, can we actually do that? Is it safe to transport hydrogen through natural gas pipelines? And under what conditions can we actually do it? What is the hydrogen purity? What is the hydrogen pressure? And this is a very difficult question to answer, particularly with experiments, because first of all, we have an almost quasi-infinite combination of pipelines and weld materials. So these natural gas pipelines have been there for 50 years. So they were installed using different materials, using different techniques. They were welded in various different ways. They also have a lot of defects, different defects. Some of them are corroded. Some of them have defects from the welding process. And of course, you also, as an engineer, you have a quasi-infinite combination of hydrogen conditions. You can play with the hydrogen purity, with the hydrogen pressure. So it's very difficult to test this gigantic amount of conditions. The other problem is that, where these pipelines are going to fail are the welds. We know that the welds are the weakest link, but welds are very difficult to characterize in the lab because you have residual stresses, because the weakest part of the weld is this kind of heat-affected zone that you see there. That is basically a very small region where it's difficult to extract samples that are large enough to do proper testing in your lab. And also, it's even difficult to test these pipelines on the real scale. People are spending a lot of money to do full-scale tests of real pipes, but they're struggling as well because you have an oxide layer, a native oxide layer that prevents hydrogen uptake. And we know that that oxide layer won't be there forever. As you fatigue load your pipe, you'll eventually rupture that layer. But it might be there for the 3 weeks that you're running your very expensive full-scale test. So it's a tricky question. So we try to answer this question with some clever experiments that I won't be discussing today, but also with some modeling efforts. And then what we want to do, and again, I should emphasize, this is group that work led by Tushar when he was at Oxford. What we're trying to do is basically to combine all those kind of coupled deformation, diffusion, fracture modeling efforts that I showed you before with some welding modeling. And we took the welding models kind of off the shelf, but I was actually quite impressed by the degree of, the precision, the accuracy, or the robustness of these welding models. I'll show you some examples in a minute. I think the nuclear community has been working on this for quite a while, and they're actually going pretty far. But the idea is simple. You first do the welding model, and then you predict the fracture. So you get residual stresses, you get phase fractions, you get, the macrostructural heterogeneity. But before I do so, of course, the first thing we did was to simulate arc curves, so crack growth resistance in those pipeline steels, with and without hydrogen. And as you can see, the model seems to be in very good agreement with the environment, so with the experiments. So that gave us confidence that the model is able to capture bulk behavior, is able to capture how pipeline steels behave in the presence of hydrogen gas. And then the next step was to simulate the welding. And again, it's not an area that we have pioneered. We just took off the shelves this welding process modeling. So you can see here the top seam weld. You can see you put this is a 2-pass seam weld. So you put the 2 passes. You see how temperature and residual stresses change within the material. This is a girth well where you have multiple passes. But the beauty of it is that we can also account for the evolution of the phase fractions. So you can see here in this well, this is again a 2-pass well. You can see here the ferrite fraction, the perlite fraction, the binary fraction, and the austenite fraction. So depending on your cooling rates, depending on your composition, these welding models have been developed that allow you to predict this evolution of phase fraction. So we can predict the macrostructural heterogeneity. And I was a bit suspicious at the beginning, saying, okay, yeah, but how do I know this is something that agrees with reality? And one thing that you can do is you can relate the phase fraction with the hardness. So then you can create this sort of hardness maps that you can compare with experiments. And you can see here, the agreement, in my opinion, is pretty good. I mean, we were basically told this is the way the welding was done, predict the phase fraction evolution, and then from there determine a hardness map, and then we'll show you the hardness map that we did in the lab. And they're not identical, but this is the same scale, and they show very similar features. So I was actually quite surprised with the abilities of these models. Again, not my model by any means. We took it off the shelf, but I was quite surprised. The other thing you can validate is against measurements of residual stresses. This is a big deal in the community now. Measuring residual stresses is quite nasty. It's not easy to do. You can see there's a lot of noise in the experimental measurement. This is with X-ray diffraction. But you can see this is for a girth well. Again, we're using exactly the same scales. We're not playing around here. We were told how the weld was done. We did the weld in the same way in the model. We plot the residual stresses. And they seem to be, I would say, good enough, or engineering good enough approximation. So I was quite excited to see this. And then what basically this allows us is to predict the variation in properties within your weld, within your macrostructure. You can see, for example, that this weld has a heat-affected zone here where the toughness is very low. So it's particularly susceptible to hydrogen. And that's a problem because people doing tests in their labs, they're testing base material, they're not testing heat-affected zone, and this is of course what's going to fail first. And then we can model, of course, the hydrogen concentration, and then you basically start increasing your pressure. That leads to an increased hydrogen concentration. The hydrogen starts diffusing through the weld, and then eventually at some point you will see that a crack appears here. So we can start ramping up the pressure slowly, and then eventually we know when the pipeline is going to fail. So then we can do that as many times as we wish, changing the welding process, changing the defects, changing the materials, changing the hydrogen conditions, the purity, the pressures, and so on. And we did that multiple times just to, again, tell you a little bit about the process. You first do the welding. You validate that the welding estimates of the phase fraction estimates are in agreement with experiments, and then you do these coupled deformation efficient vector simulations. And I'm not going to discuss the outcomes for the sake of time, but this is the kind of things you can do. Out of the welding process, you have a lot of defects in place, so you can put those defects into your model, and you can see how hydrogen will lower those. So standards will let you do welds and get away with certain types of defects. Whether those defects are going to be problematic when you bring hydrogen or not, that's the good question, and a question that you can answer with the model, and that is very difficult to answer with experiments. And of course, what we found, among other things, is that pre-existing defects play a big role, as you would imagine. So we tried to do a systematic characterization of those pre-existing defects, and we found that Tushar found that if you align a 3 millimeter crack along the heat-affected zone, the critical pressure which your pipeline will fail is 15 megapascals. And that's problematic because this is one of the pressures they're considering for hydrogen transport, and because they know they have defects like this, they know from pipelines taken out of service that they have defects like this in the same weld. And what is interesting is that 3-4 months after Tushar published his paper, they did a full-scale test when they introduced with EDM a notch of these characteristics in a full-scale pipe, and they applied some fatigue to break the oxide layer, and they found the critical pressure to be 12 megapascals. So Tushar's predictions happening months before was actually in relatively good agreement with a full-scale test, with all the uncertainties that come with those things. Okay, so that's all when it comes to hydrogen, and in order to finish on time, I'm going to move swiftly to the battery part. I don't think this needs a lot of motivation. You all have lithium-ion batteries in your phones, in your laptops, so you're all familiar with all of this. The mechanisms are quite simple when it comes to degradation mechanisms. Every time you charge your battery, you have lithium ions going from these cathode particles to these anode particles, and every time you discharge your battery, you have lithium ions going from the anode particles to the cathode particles, and then electrons going the other way around. And every time you charge or discharge your battery, what happens is that those lithium ions are stored in these anode and cathode particles, and this lithiation process breaks some deformations. You have swelling and shrinking of those particles with every charge and discharge that you're doing. And that continuous swelling and shrinking of those particles leads to cracks, and this is the main degradation mechanism in lithium-ion batteries. This is the reason why you need to replace your laptop or your phone every 2 years or so. So of course, again, what do we find in front of us? a couple problem that is deformation, diffusion, fracture. And that is multiphysics, and that is well suited for multiphysics modeling. So we decided to tackle the problem in the same way. The good news is that the equations are almost the same. So you have an equation for the deformation of the material, one for the damage. Here you notice that the lithium concentration does not degrade your toughness. People have done atomistic simulations and have seen a little bit of degradation, but very little, nothing to do with hydrogen. Hydrogen really makes easier to break bonds. It's not the case with lithium. And the other thing that you see is that you have these chemical strains that are very small in hydrogen, but are very prominent in lithium. And this comes naturally out of the model. So we had it in the hydrogen model as well. It just becomes negligible because your model depends on physical properties. So you have this partial molar volume that is a quantity that we know, that we have measured independently, decades ago, that is well established. So when you have this kind of physical model, you don't need to make any assumptions on what are the physics happening. You just put the real parameter values and the model will tell you what's happening. And this is the main problem. We have these chemical strains. In fact, in these batteries, we're not applying mechanical load. It's just the charge and discharge, the lithium ions coming in and out, that are causing the swelling and the shrinking of those particles through those chemical strains. So you can capture in the model. And then what we did, a few groups have already worked on this with phase field, but they only look at a half cycle because they didn't have a fatigue model. So we had the fatigue, and we simulated hundreds of cycles, which is the scale relevant to these problems. And we modeled not only idealized particles, but also realistic particles working together with people working on XCT scanning. And then basically you can charge, the way you charge those particles. And basically, again, at the end of the day, you have a virtual platform where you can play around. You can change the shape of the particle, the defects. You can change also the way you load your particles. And therefore, you can quickly map what are the conditions under which things will be safe. Particle cracking will not occur. And now we are also using this to test new theories. So again, let me emphasize, our goal with these mechanistic models is twofold. First, we want to map safe regimes of operation, understand under what conditions will be safe and sure. And then the other reason is that we want to test ideas quickly. How can we develop the next generation of batteries? For example, there's a lot of interest now in core shell structures. So we've extended the model now to account for this kind of core shell structures and see when these debonding or fracture processes will take place. But not also, we'd also look into a single electrode particle like other groups have done, but we have taken this to the next level, to the electrode level. And this is together with a group of Paul Sharing. They're very good at XCT scanning, so they can do full XCT scans. We can segment those XCT scans so we can determine not only particles, but also secondary phases, pores, carbon binders, separators. We can combine those, we can segment those XCT images, and then we can run our phase field simulations. And just to show you some representative results, what we see here, this should be plain, I think. So what we see here is distribution of damage here, lithiation of lithium, so concentration of lithium and hydrostatic stresses. And then we can use our model to, this video is not showing well, but anyway, this is what is expected. So you have this, basically the video is just showing this, you have particle cracking along your component. So you can use this tool, for example, to answer questions related to the heterogeneity of the electrochemistry. So people discuss what is the ideal electrode thickness. You can test the electrode thickness. What is the role of secondary phases, and so on and so forth. And you can also take it down the scale. So there's a big discussion now. I think they say Tesla is going to come up with a million cycle battery, which apparently is based on replacing those grain structures by a single crystal. Because of course, grain boundaries are the weakest link. So if you replace those grain boundaries by a single crystal, maybe you get a super battery. We can test those ideas with those models. So we can, again, in combination with these very nice XCT facilities that they have, we can we can resolve that microstructure into the model. We can make the phase field grow only along the grain boundaries. You can distribute properties around, and we can do the simulations and predict what will be the evolution. And then we can play games. We can see what is the difference to having a single crystal. We can also change the microstructure. Maybe you have a graded microstructure where grains are smaller on the outer side, bigger in the inner side. All of those things you can do quickly with this type of models. And then finally, the last item I want to discuss with batteries is what we call all solid-state batteries, which are supposed to be the next big breakthrough in battery technology. And the idea is that by replacing a liquid electrolyte, not only you gain in safety, you replace something that is flammable by a solid electrolyte, but you can also use lithium metal as the anode, and that will give you an order of magnitude higher capacity. So this is what everyone is working in. Toyota has already made claims that they have one solid-state battery out there. Another, I think Mercedes or BMW have also said something along those lines. But it's still yet to be seen. No one has seen a commercialized version of these solid-state batteries. And the reason we cannot commercialize these solid-state batteries is mostly mechanical problems that occur at the interface between the lithium metal anode and the electrolyte, the solid electrolyte. And the main problem that we have is these dendrites, basically. These are kind of needle-like structures that are generated in the lithium metal and they grow all the way into reaching the cathode and therefore cause the short circuit of the battery. You can see an image of those dendrites being formed here. So here I'm rotating the battery. So this is the electrolyte. And you can see how those dendrites grow through the electrolyte until they get the cathode, and then you get short circuit of your battery. And initially, the battery community was very interested in, can we stop those dendrites? So they have polymer electrolytes, and they replace them by very stiff ceramic electrolytes, thinking that maybe those stiff ceramics will block the dendrites. But that didn't happen. Dendrites continue to grow. So what we focus in my group is, can we try to predict the nucleation of those dendrites? And for that, what we do is, well, basically what happens is what you see here. How are those dendrites formed in the first place? You see it here. These are images from Peter's group at Oxford. So initially you have an interface that is quite smooth. It's not perfect. Nothing is perfect in life. But you have your sodium or lithium metal, and this is the electrolyte. Every time you discharge your battery, you do stripping. So you take away your lithium ions, and then you generate voids. It's kind of corrosion. You're removing material. And ideally, you want to remove it uniformly, but because your interface is non-uniform, you are generating those voids. And then when you charge your battery, you have plating. You deposit lithium here, and therefore you see that those voids kind of shrink in size, and even they get occluded from the electrochemistry you see here. And those voids are critical because at the edges of those voids, you're going to have localized regions with very high current densities. And in those very high current densities, you're going to have growth of dendrites, the nucleation and growth of those dendrites. So we need a model that is able to capture how those voids evolve in time and how those current hotspots will be formed to determine whether we reach a critical value of current or not. So again, this is a very suitable problem for phase field. We're not talking about fracture anymore. The interface that we care about in this case is those voids changing shape. So it's the lithium metal void interface. But we have another electrochemomechanical problem, another couple problem. So we develop a theory where you account for, for the interface reaction. So kind of sort of the corrosion problem, right? Every time you do stripping, lithium ions get detached from the lithium metal. Every time you do plating, you deposit those lithium ions back. You need to capture that. We capture that through suitable interface reactions. You also have lithium diffusion within the metal, vacancy diffusion. Again, you can couple that with a transport problem. You're voiding, so a nucleation and annihilation of vacancies that generates voids, and those voids are going to evolve in time that you can capture through the phase field mechanism. And then mechanics. Mechanics plays a big role, not only due to lattice distortion, due to the transport, like the chemical strains that we discussed before, but also because the main hypothesis in the battery community is that in order to prevent those voids from growing, we can apply a stack pressure. Lithium metal is like toothpaste. It's very soft, so if you apply a stack pressure, you'll close those voids. So that's something we can test just to get a flavor for the boundary value problem that we saw. We have the lithium metal with some voids. You have the electrolyte, and we're solving an electrochemomechanical problem, so we have the electric field. So we're going to see naturally those corrosion current density distributions. You're solving a phase field problem for the voids, transport problem, a mechanical problem, and then some electrical problem. And these are some representative results. This is for stripping. So I'm removing the lithium. And you can see, on the left, I'm showing the phase field contour. So this is the lithium metal anode. Red is the lithium metal. Blue is the void. And on the right, I'm showing the current. And you can see how not only the model captures, the expansion of the void, looking similar to the SEM images that I showed you before, but also how the current localizes at the void edges. And therefore, you naturally capture those corrosion. We are not putting any criteria. We're just solving the couple problem. And the model tells you, oh, you have a lot of current down there. And when you do plating, it's the opposite effect. You are depositing lithium, and the model is able to capture how the void diminishes in size, how those hotspots eventually disappear, and how you get eventually even the occlusion of that void that we saw in those macroscale experiments. And now what we're doing is looking at more realistic cases. So we apply a pressure. We see what pressures we need to enable a solid-state battery breakthrough. We put multiple voids. We do multiple cycles of charge and discharge, and we also use this to test ideas, new interfaces, new cell geometries, and so on and so forth. And one last thing I'll say is that together with colleagues at Georgia Tech, we also look into what they call anode-free batteries, where you basically you create your lithium metal anode by the first plating step. And we saw that, depending on how homogeneous that lithium plating step is, you get a very different behavior with the model. And they show that then later with experiments. Okay, so I'm going to finish in 5 minutes, I promise, looking at corrosion. Corrosion, again, needs little motivation. You're all familiar with corrosion. My bike is always corroded. Maybe yours is too. And I think one of the things that I'll say about corrosion is that not only is a gigantic problem for everyone, but it's also a problem that, has eluded scientific and engineering efforts. We have learned a lot through careful experimentation about corrosion, but we're still unable to predict corrosion failure. So corrosion failures continue to happen, in very well-developed countries with very rigorous standards, just because we don't have a model capable of predicting when things are going to fail. So it has eluded all us computational scientists. But I think there's an opportunity here to couple this. And every time I talk to corrosion scientists, 95% of them are experimentalists, and they tell me, corrosion is a too complex model to be simulated with computers. And they're right, there's many things that happen in corrosion. So if you think of, for example, the corrosion of offshore wind turbine monopiles, this is driven by pitting. How those pits, how that corrosion front morphology is going to evolve is going to depend on the local chemistry and mechanics, which is going to depend themselves on the shape of those pits. So everything is very strongly coupled, and there's many things happening in there. But again, a coupled multi-physics problem and an interfacial problem. So why not use phase for this? And then if you think of the simple phase field description of corrosion that you're interested in, we no longer care about cracks. Now the phase field is going to tell me whether I'm in the electrolyte or in the corroded metal, and it's going to vary smoothly in between. And then you need an extra variable, which will be the concentration of metal ions, which will be equal to 1 in the normalized way in the metal and 0 far away from the electrolyte. So you generate those metal ions, and that allows you to capture the interplay between activation and diffusion control corrosion. So basically, the simplest model you can think of, there's many other things, there's mechanics, there's other things, but for the time being, the simplest model you can think of has two equations, one for the short range interaction, so material dissolution, atoms being detached from the metal, so to say. That is captured with the phase field model, the Alencamp type of equation. And basically the parameter that matters is the L, the mobility coefficient, and we have shown that that mobility coefficient is proportional to the corrosion current density. So again, a parameter that you know before you run your calculation. And then the other one equation is a transport equation type of fixed law, where you capture the transport of those metallic ions, the long range interactions, that relies mostly on the diffusivity, which is again a material property that we can measure independently. And let me show you how it works. So this is a pencil electrode test. So this is a simple 1D example where you basically have corrosion of the metal happening in a uniform way. And you can see an example. So this is the model showing how the corrosion front evolves in time. And this is the distribution of metal ions, which is the highest at the interface. And then they just go away into the electrolyte, basically. And the good thing about this very simple 1D problem is that you have an analytical solution, a lot of experiments that we can also validate. But you have an analytical solution for the case of diffusion control corrosion. And you can see that the model seems to agree quite well. And you can also show that the model can naturally capture the transition from activation control corrosion to diffusion control corrosion. You can see here, this is the linear behavior typical of activation control corrosion. And then eventually, if you ramp up your corrosion current density, you get to this regime of diffusion control corrosion. Without having to make any criteria, any decisions, just the model will capture that naturally. And then, just to conclude, I would just say that my experimental friends who work on corrosion are right. Corrosion is a very complicated problem. There's many, many things happening. But I think that this kind of mesoscale finite element models can handle all of those things. And computers are finally big enough that we can resolve those processes. So you may have secondary phases that are insoluble, interaction between multiple pits, intergranular corrosion. We recently done some XCT 3D observation. I've shown some very interesting phenomena. We can again rationalize this with this. And it's not only the computational things that you need to do, it's also the physics, right? There's a lot of things happening in corrosion. You may have an influence of the electrochemistry, but again, we can solve those equations describing electrochemical behavior of electrolytes. You may have microstructural isotropy. Again, you can couple this with crystal plasticity, with microstructural descriptions of your material. Mechanics plays a big role, discussed very briefly now. You might have hydrogen ingress as well, so the kind of generalized stress corrosion cracking. You can couple these corrosion models with everything that I showed you before. And then you may also have, for example, other products, corrosion product formation. Again, you can have a phase field model that can capture the formation of those oxides and secondary products. So everything that you can think of, this is kind of mesoscale electrochemomechanical physical phenomena you can incorporate into your model. And I'm running out of time, so I'll just skim through quickly, but I'll just say things that are of interest to us, the way we have extended this framework, because I think this, I guess the takeaway that I want to say is that this is a completely new field. The models are not as mature as the fracture or hydrogen embrittlement models. But I do think there's a very good opportunity. I see this field growing very fast, and I see that it reminds me a little bit maybe of the early days of phase field for hydrogen or phase field for fracture. So I think this is a good opportunity as a scientist to start working on this field. And so we try to contribute to this community. I think it's fair to say that we were one of the first groups to do these things. And we were the first to incorporate the role of mechanics. Mechanical fields can enhance corrosion kinetics. We know that there's an expression derived by Goodman. So we can incorporate that into our model by enriching this mobility coefficient, and then we run virtual experiments, and you can see that we get a very good agreement with experiments for 2 different levels of applied load, not only in terms of the degree of corrosion, but also the morphology of the corrosion front. So there's multiple, these images on the same scale, and there's multiple pits. We model only one, but it looks to be in good agreement. There's also the film rupture mechanism process. Those of you, I'm not going to have time to explain it, but those of you familiar, you know that mechanical fields will rupture the passivated film that prevents some metals from corroding, like stainless steel. So we are able to capture this. You can solve for a mechanical problem as well, and you can accumulate strains and decide when the film is ruptured. And when you do that, you see kind of this pit to crack transition phenomena. You can capture very well this interplay between repassivation and straining kinetics. The microstructure also plays a role. We know that there's not only the mechanical crystalline isotropy, but also there's a corrosion rates and isotropy. So we can define a grain orientation dependent corrosion potential, and then we can do simulations and basically compare with the isotropic case and understand under which cases we need to resolve the microstructure, creating maps like this one, but also understanding what happens with 3D printing materials where you have different microstructures. Are they more or less resistant to corrosion? How does the resulting microstructure play a role in those cases? The electrochemistry is something that you can incorporate, and now we're just being greedy, throwing all the equations that we want. But computers are big enough. Again, we know the Nernst-Planck equations. We can solve in there. We can solve for as many ionic species as we care about, and then we can see effects of solvent concentration, applied potential. We can see how the field degrades. And then the last thing that I'll say, and I want to say it because I know I'm running out of time, but Tusha was involved in this as well. We just have a paper recently accepted in Acta Biomaterialia this year, where Tusha is a co-author. And the idea here is what we call biocorrosion. So here the problem is that we want to, if you break your leg, they're going to put an implant on you. This will normally be made of titanium, and this implant you'll carry all your life. And that's not a big deal. I mean, it'll be a problem when you go to an airport, but otherwise it's fine. But in kids, they need to do a second surgery to remove the implant. So we want to avoid that. We want to produce implants of biodegradable materials, biocompatible and biodegradable materials. And the key here is this graph here. So you want as your bone or your tissue heals, you want your material to degrade. And the problem with magnesium is that it degrades too fast. Magnesium is the most promising candidate, but it degrades too fast. So we need to understand the corrosion of magnesium. So for that, we again extended the model. And as you can see, we compare with experiments, not only with simple lab experiments, but we can also use the model to predict the evolution of full-scale implants, screws, or stents, as you can see here. And I think one of the strengths of the model is that because we cannot do experiments on humans, we can check that the model works well against in vitro conditions, against lab experiments, and then simulate in vivo conditions, how the human is going to behave. That's the takeaway. For those, since this is a civil engineering department, those of you interested in corrosion in reinforced concrete structures, we also look at this. You can do with these models corrosion in the natural conditions, atmospheric corrosion, no need to apply a potential. So you can interpret accelerated tests and predict what's going to happen under real conditions. Again, I'm running out of time, so I'm going to skip this. And then finally, the very last slide, you can also couple this with all the hydrogen embrittlement that you had before. So you don't need to make any assumptions on whether the fracture in this stress corrosion cracking condition is going to be driven by hydrogen, by anodic dissolution, by a combination of both. You have all the physics in your model, and you let the model do the job for you. And with that, you can capture toughness as a function of applied potential for a wide range of conditions. Okay, and just finishing just on time, some concluding remarks. I will just say that, I think we do have a very exciting opportunity in front of us. I think that the combination of phase field modeling of interfaces and this kind of coupled multi-physics models allows us to finally resolve the underlying physics of many complex phenomena, such as, fracture, voiding, and the evolution of the corrosion front. And the good thing about it is that, you eliminate assumptions, you eliminate fitting parameters, and you can deliver predictions that are basically resolving the underlying physics as they happen in reality. And I think that's quite exciting because, again, you rely purely on physical parameters that you know before you run your calculation. And that allows you to deliver predictions at scales relevant to engineering practice with confidence. And I hope to have convinced you that the combination of these two ideas, phase field plus multiphysics, can allow you to gain new insight into the failure of materials exposed to hydrogen. And I'm happy to say as an engineer that some of the models that we develop are being used now to decide under what conditions to transport hydrogen in natural gas pipelines, or to design pressure vessel steels for storing hydrogen. So they know the parameters come before you run the simulation, you have confidence in them. But we've also shown that you can combine these models to predict the degradation of battery materials. And again, We're now working with industry to develop solid-state batteries based on these models. And finally, the corrosion of metals in aggressive environments. But again, the collaboration with industry is strong. We are working to, there's a big European project based on those biocorrosion models I showed you before, but also we have a student funded by the nuclear sector to try to predict nuclear waste canisters, under what conditions they will corrode. They need to know how they will corrode in thousands of years from now, so they need a model, but also with offshore wind turbines manufacturers and operators to determine when they need to replace those offshore wind turbines. That's all. I'll just finish by saying that all the codes that we develop are openly shared. So all the results that I showed you today, you can go to our website, you can download the code, and you can reproduce everything that you showed today. And if not, send me an email, I'll be able to help you. We have developed codes in a variety of platforms. We work a lot with Abacus. COMSOL has also now implemented and built most of the things that I showed you today, like facial fracture, for example, and hydrogen embrittlement and so on. So just click a button and you can run those simulations, even if you have no computational mechanics expertise. And we also develop our in-house codes in MATLAB, C++, Phoenix, Julia, and others. That's all.